What is special about neutrons that makes an atom more or less stable depending on how many there are? Is it magic? Because I think it's magic. That's a great question. And there is actually something to do with the word magic when we talk about the number of neutrons that you have in a given element. Now, in the same way that you have noble gases occur when you have filled an electron orbital so that the electrons are as packed as they can possibly be. And one more electron will require that it's much further out because it's a new orbital. We have magic numbers in the nucleus where we've got filled orbitals of protons and neutrons, and putting another proton or neutron in there is going to have to go into a whole new orbital and make it substantially bigger. And so those nuclei that have those magic numbers of protons and neutrons are the ones that are most compact. Now, what's unique is that protons and neutrons are distinguishable. And so by the laws of quantum mechanics, they can, for all intents and purposes, be in the exact same orbital. A proton can basically be in the same orbital as a neutron because there's a difference in charge and a slight difference in mass. And so as you're building up the different isotopes with protons and neutrons, you're filling different orbitals. You're starting at the lowest orbital that you can have. And the way that those are attracted to each other is called the strong nuclear force. Now, the strong nuclear force, the best analogy I can come up with is like a water molecule. When I have water together, a water molecule will be attracted to another water molecule near it because of polarity. There are polar molecules. But a water molecule won't necessarily be very attracted to two molecules over. It's really only interacting strongly with its nearest neighbors. And that's basically what the strong nuclear force does. It's not the same as polar, but it gives the same effect so that for large nuclei, you actually get like a water droplet effect. And what that means is that the lowest energy modes that you can excite by dumping energy into it are vibrational. And they're the same vibrational modes that you get for a water droplet. And that's because this attraction, this nearest neighbor attraction inside the nucleus, it's analogous to water. And so there's actually a water droplet model that we use for the nucleus when we describe the interaction mechanisms that you see. Now, the actual attraction force is called the strong nuclear force, and neutrons have it and protons have it and they share, but it's very short ranged. It basically just goes the range of, say, a proton or a neutron. So again, it's really just nearest neighbor type of physics. And when I have these orbitals filled, if I dump more energy into it, I can excite a nucleon, a neutron, or a proton to a higher energy level. And when it falls back down, it gives off a gamma ray. That's how we define a gamma ray. It comes from energy transitions in the nucleus. And so a stable isotope is one where the right mix of neutrons and protons are there. If you don't have the right mix, if you got too many neutrons or too many protons or vice versa, then it's going to decay by either giving off particles or energy in the form of, say, gamma photons and or beta or alpha or even positrons possibly. There are other decay modes that are there, but that's basically the idea, is that exciting the nucleus to higher energy levels so it gives off a gamma, that's comparable to fluorescence in an atom, where I excite an electron to a higher energy level and give one off. That gives off a photon of light. If it's a deep shell electron, then that would be an X-ray. If it's a transition in the nucleus, then it's a gamma ray. And so I hope that answered the question. It's not magic. It's just attraction forces as are found in nature. And thanks for the question. Thanks for watching the video. Have a good day. Bye.